Welcome back. This is the review video for complex numbers. Let me start with the basic idea of complex number. You know what it is. It's usually denoted as I, which is equal to square root of -1. So I square would be -1 and I cube would be -1 times I, which is minus I. So I to the power of 4 would be, I can take it as I cube times I, which means negative I times I, which is negative I square, and we know that I square is -1, so negative I square is +1. So I power 4 is +1, I cube is negative I square is -1, and as I is equal to root of -1, and you can continue like this. So you have to be you should be having some idea about this. First of all, what is I square, I cube, I power 4, at least up to power 4. Now, a general form of a complex number is always a plus ib, and this a and b are any two real numbers. It could be 0 as well. So when a is 0, you get ib, which is called a purely imaginary number, and if b is 0, you get a, which is a pure real number. Okay, this is imaginary number and this is a pure real number. So in fact 2 is a complex number because you can write a 2 as 2 plus I0. So it's of the form a plus ib, therefore 2 plus I0, which is 2, is a complex number. So all real numbers are complex numbers. And different notations, different properties of complex numbers. If I have two complex numbers, a1 plus ib1 equal to a2 plus ib2, then a1, the real parts are equal and the imaginary parts are equal. Okay, you can equate the imaginary parts and then you can equate the real parts together. So where is it used? If you have say for example cos theta plus cos 2 theta plus cos 3 theta or something, and plus I times sine theta plus sine 2 theta plus sine 3 theta, and if this is equal to 2 plus 3i for example, then you can equate this to 2 and this part to 3, which means that cos theta plus cos 2 theta plus cos 3 theta is equal to 2, and sine theta plus sine 2 theta plus sine 3 theta would be equal to 3. So this is some cases where you can use this property. When two complex numbers are equal, the real parts are equal and their imaginary parts are equal to each other. Also, you can have some cases like cos n pi plus I sine n pi equals 3 plus 4i over 5 maybe. Then you can say that cos n pi equals 3 over 5 and sine n pi equals 4 over 5, and therefore you can find what n is. So in these cases you are using this property where you equate the real parts and the imaginary parts. Okay, the next is other ways of representing complex numbers. This one is simplified to cis theta, that is capital C, small I, capital S, and a theta, which means cos plus I sine theta. Okay, so cos theta minus I sine theta is written as cis minus theta, because cos of minus theta is cos theta and sine of minus theta is minus sine theta, and here it is e power minus I theta. So these are certain notations that you should be knowing. Also, if usually z is the letter given for any complex numbers, if z is a plus ib, then the conjugate could be written like this or like this, is equal to a minus ib. Only the imaginary part is negated. So even if you have something like minus 2 plus 3i, then its conjugate is minus 2 minus 3i, and if it is 2 minus 3i, then it would be 2 plus 3i. Okay, so you basically you change the sign of the imaginary part. If you have say minus 5i plus 2, then it's not necessary that you should change the 2. You have to change it as 5i plus 2. It's always the imaginary part wherever it is placed. Okay, and then next is about modulus. The modulus of a complex number is written like this, which is a plus ib, and which is actually square root of a square plus b square. You can always represent or think about a complex number as a vector, which is as a position vector of the point AB. So this is a plus ib. Okay, the point a comma b is actually a plus ib. So you can see that the modulus, this is z. So the modulus of z is, sorry, not bar, modulus of z is square root of, this is a and this is b, therefore this is square root of a square plus b square, which gives you the modulus, that is the length of this vector. So it's the same thing as vectors. You can always combine the vectors and complex numbers in any way. So basically speaking, a modulus is a square root of the real part, whatever it is, even if it is negative or positive, real part the whole square plus imaginary part the whole square. Okay, so you can see that you are if you have say 3 minus 2i, then it is square root of 3 square plus minus 2 the whole square, which is equal to whatever, 9 plus 4 and so on. And do not make this minus. This is never minus. The minus goes within the square. Okay, that is one thing that you need to know for not making any silly mistakes. Okay, that is very common mistake that people make. There is no minus sign in between x square and y square, that is a square and b square. Okay, next comes what is argument. There are two things here. One is called principal argument. This is which is very important, principal argument, which is always between minus pi and pi. So it's always like this, minus pi, 0 to pi here, or 0 to minus pi. So when it is at pi, you can use always pi, you need not use minus pi. So when it is pi, you always go from this side to here, so that you take it as positive pi. But when it is negative, you go from 0 to negative pi. Okay, I think that's clear there. And how do you get these angles? So I told you a complex number is just a point on the coordinate axis. So if you have a plus ib as your complex number, then if a and b are here in this quadrant, then both a and b are positive, so you have your complex number in this quadrant. If a is negative and b is positive, then your complex number would be in this quadrant. In this case, you'll have negative a and negative b, in which case your angle would be, principal argument would be negative. Even in this case where you have positive a and negative b, the principal argument would be negative. So in these two cases, the principal arguments are positive, whereas in the cases below the x-axis, the principal arguments are negative. So we can do some 1 or 2 questions of this. Let's find the principal argument of 1 plus I. So how do you find this? This is basically you need to find the tan inverse, arctan of if you have a plus ib, then the argument is tan inverse of arctan of b over a. So in this case it is tan inverse of 1, which is pi over 4. And how do you mark it? This is both positive, therefore it should be pi over 4. Okay, and if you have minus 1 plus 2i, then your argument is tan inverse of 2 over minus 1. So which means that it is negative. Tan inverse of 2 is 63 degrees 26 minutes. It doesn't mean that it's in the first quadrant. So you have a negative a and positive b. So this should be here in this quadrant. Therefore, you cannot take it as, this is where it is. You cannot take this as 63. So this is 63 degrees. 27 minutes. Therefore, you need to find the angle from this part only. Therefore, you have to subtract it from 180 degrees. Be careful with your calculator mode, whether it is in degrees or radians, and accordingly give the answer. Okay, so your answer here is 116 degrees 34 minutes. So this is the angle which we are looking at, because always the angle starts from 0 of the positive x-axis. Okay, so this is the angle for minus 1 plus 2i, and don't stop here, you will not get full marks. Okay, and one more question on this: minus 1 minus root 3i. Obviously this is in this quadrant, therefore the angle should be negative. This would be tan inverse of square root of 3. I would like to say here, in this case, while you are finding the inverse, do not consider the negative sign. You consider tan inverse of 2, and then check for negative sign only for seeing whether you need to subtract or you need to give it directly. And in this case, again, as I said, you don't worry about the negative sign. Just take the numbers here like this, and then it is tan inverse of square root of 3, which is pi over 3, 60 degrees. But the 60 degrees is here. This is 60. So what you have to do is you need to actually find this value, which is negative. So this is actually 180 minus 60, which is in the negative side. 180 minus 60, and you need to put a negative sign because we are going towards the clockwise direction. Therefore this is minus 120 would be our actual angle, which is this one. A few minutes before we were talking about the conjugate a minus ib for the complex number a plus ib. Where is it? Where is this used? Usually it is used when you have two complex numbers in quotient form. So in order to take away the complex number in the denominator, you multiply the numerator and denominator by the conjugate of the denominator. So whenever you want to take away the complex number, multiply and divide by the conjugate, because when you multiply two conjugate, complex number with its conjugate, you get this a square, a plus b, a minus b. Therefore this is a square minus ib the whole square, which becomes a square plus b square. So you can see that on multiplying the conjugate with its complex number, you are getting rid of the I there, so it becomes a real number, pure real number. Therefore, in order to get rid of the complex number in the denominator, you take the conjugate of the denominator, multiply the denominator by its conjugate, which means that you need to multiply the numerator as well. So you have a complex number in the numerator, but you have a real number in the denominator. In denominator would have c square plus b square, and you'll have a complex number in the numerator. So this is where we normally use the conjugate property of a complex number. I also said that a complex number can be viewed as a vector. So if I have z1 as some number a1 plus ib1, and z2 as another complex number a2 plus ib2, then I can actually make 2 points a1 b1 and say a2 b2, and these two are my vectors, which is also the complex numbers. So z1 and z2 are here, and you know that modulus z1 is the length of this, and modulus z2 is the length of this. So what about z1 plus z2? Geometrically it is the resultant of these two, like you do it for vectors. Sorry for the diagram. This is a plus b, which is z1 plus z2, while this one is z1 minus z2. So it can be viewed the same way as you do for vectors. So that's the point in this explanation. We found what is argument of a complex number, and we know what is a modulus. So argument is denoted by theta and modulus is by r. So we also noted that cis theta is one of the forms of complex number. So this form is called polar form. This is known as polar form. So you can convert any complex number into polar form. So if modulus is equal to 1, then you have cis theta. If modulus is not equal to 1, then you have r cis theta, which is r cos theta plus I sin theta. So usually this is called the polar form with r not equal to 1. If it is equal to 1, it's just cos theta plus I sin theta. Now how will you convert a plus ib to r cis theta form? That's what we are going to do now. We'll take an example of minus 1 minus I. So you need to first find what is theta, the principal argument, and the modulus. The modulus is square root of 1 plus 1, which is square root of 2. Theta is tan inverse of 1, which is pi over 2, which is pi over 4. And now you need to find where the principal angle is, because it's both negative, so it should be in this region, which is supposed to be actual value of the principal angle would be minus of pi minus pi over 4. We just did this, which would be minus 3 pi over 4. Okay, this is your theta. So your polar form for this question would be square root of 2 cis minus 3 pi over 4 is actually minus 1 minus I. So you can actually plug this in to the calculator and see whether you are getting this answer. 3 pi over 4 plus I sine minus 3 pi over 4. So if you substitute the values of theta as 3 minus 3 pi over 4 for cos and sine, you will be getting this minus 1 minus I as your answer. Now how do you do this for purely imaginary and purely real numbers? Say if I have 5. I said 5 can be taken as 5 plus I0. So what is the argument of this? Tan inverse of 0 over 5, which is equal to 0. So again you can see that it's on the, usually it's on the real axis on this place. So this is the place where the complex number is placed here. So this means that argument is 0, and we don't usually take it as 0 because you go around and you can take it as 2 pi. So you can write this as 2 pi, or you can write it as 0 here, depending upon the question. If the question is asking for with an angle from 0 to 2 pi, then you can use 2 pi. If not, if just argument or principal argument, then you are not supposed to use 2 pi here. You are supposed to use pi, so that your radius, that is the modulus, would be 5, because it's square root of 5 square plus 0 square. Therefore this is cis either 0 or 2 pi. So this is the polar form of 5. And the polar form of say 2i would be 0 plus 2i actually. So tan inverse of 2 over 0, which is infinity. Therefore the argument would be pi over 2. Therefore it is cis pi over 2. But your modulus would be square root of 0 plus 2 square. Therefore this is 2. So 2 cis pi over 2 would be the answer for 2i. So in short, any complex number can be written as r cis theta. So if I have one complex number, then it's r1 cis theta 1, and the other can be r2 cis theta 2. So how do you multiply and divide these two? If they are in terms of polar coordinates, then z1 times z2 would be r1 r2. This is a formula, theta 1 plus theta 2, and z1 over z2 is just r1 over r2, but the arguments would be subtracted. Remember this because you don't have this in your information booklet. So if it was not in polar form, I have already discussed, you can see you can easily multiply and divide. For multiplying, I can use 1 a2 plus ib2. For multiplying, you can just multiply term by term as you always multiply in algebra. For division, you need to go for conjugate of the denominator. So you can just multiply by the conjugate of the denominator and get the complex number there. So that is known as Cartesian form. A plus IB is always called the Cartesian form. Now going for the most important part of complex numbers, De Moivre's theorem. This states that if you have r cos theta, I'll put a bracket here, plus I sine theta to the power of n, whole to the power of n, then this is r to the power of n cos n theta plus I sine n theta, and again r power n comes out. So this is the actual De Moivre's theorem. This n is applicable for any positive or negative numbers, even for rational numbers, so which is 1 over n. We'll be seeing that soon. You don't need to do the proof of this, but we can do some questions on this. Let's say 1 plus I root 3, okay, whole to the power of 5. We need to find this. How do you find this? First of all, you need to convert this to polar form, or cis theta form. So you need to first take z equal to 1 plus I root 3. And then you need to find the theta, which is tan inverse of root 3 here. Both are positive, therefore it is the direct answer, which is pi over 3. Now modulus is square root of 1 plus 3, which is square root of 4, which is 2. Therefore the cis theta form would be 2 cis pi over 3. And then z power n would be, z power 5 here would be 2 to the power of 5 cis 5 pi over 3, because the whole power 5 becomes n pi over 3, which is 5 pi over 3. So which is on expansion, it is actually 2 power 5 cos 5 pi over 3 plus I sine 5 pi over 3. And you check the question. If you are asked, if the question is find the value of 1 plus I root 3 to the power of 5, then you better give the answer in the same form, in Cartesian form, which means that you need to plug into your calculator these values and get the values and give them as real numbers. So final answer should be in real number a plus ib form if your question is in this form, or even if the question is specifically asking you to give the answer in this form. So please be careful what the question is all about and how you are expected to give the answer. If it is not so, then you can leave the answer in this way. I would continue with this. It would be 2 to the power of 5 cos 5 pi over 3 would be, pi over 3 is here, 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, and the fifth pi over 3 would be on the same place as pi over 3. Therefore, it's the same value as pi over 3. Even if this is a paper 1 question, you can always do it without calculator. So this is same as pi over 3, which means cos pi over 3 is 1 over 2 and sin pi over 3 is root 3 over 2. So you can see that this is just like 2 to the power of 4 plus I times 2 to the power of 4 times square root of 3, and this is of the form a plus ib. So this is as easy as that. So you can easily find out the power of any complex number, the complex number to raise to the power of any natural numbers. Okay. But you can also, if it is paper 2, you can actually find directly, plug into your complex into your calculator what is 2 plus 3i power 8, and you will get the answer in a plus ib form. So that's not a problem if it is in paper 2. But again, look into the marks. If you have really good number of marks, please you use calculator only to check your final answer. So if this is a question in paper 2, then you might have to find what is tan inverse of 3 over 2, and you may have to find what is 2 square plus 3 square square root of, which is 4 plus 9. You can keep it as square root of 13, but in case if you are supposed to give the answer in decimal forms, then you might need to use your calculator. Then I insist that you use calculator only for this and for finding this in case it is necessary, but you better keep this as square root of 13 till the end. But for finding tan inverse of 3 over 2, you need your calculator. Therefore please do this step by step, and you need use your calculator in this place, and then find the value for tan inverse of 3 over 2, and then continue as we did in the previous question. But at the end, you can always check with the direct use of calculator. Another important thing is when you are using GDC in between, please do not round off the answers in between the steps. Do not. Okay, don't do this, because rounding off in every step rounds off the final answer to an extreme level that it goes away from the answer expected in your marking scheme. Please do not round off. Use at least 5 to 6 decimal places, or use the actual number from the calculator directly, and plug in into the next few steps. And final answer, you give the full answer, say 2.45646 dot dot dot, and then you give another answer like 2.45, and then finish it off with this plus I 3.564 dot 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 dot, and then the next step you finish it off with three significant figures, or to say do two decimal places, as and how the question goes. Okay, please be careful using the GDC at this in these questions. Do not round off in between. Now there is also another important application of De Moivre's theorem, which is finding the roots of a complex number. Which means, what is a root? Root is, if I have nth root of a, then it is a to the power of 1 over n. So that is the same thing. Nth root of a plus ib is a plus ib to the power of 1 over n. So we use the same De Moivre's theorem. A plus ib should be converted to r cis theta, and to the power of 1 over n would be r to the power of 1 over n cis theta over n. But in this case, there is something very important here to note, because when you square a number, you get one value, but when you find the square root, then you get plus or minus two values. So you can take this as a very simple case to understand that when you are taking the roots, then you can have so many values as the number of the third has. If you have cube root, then you have three values, but when you are cubing something, you have only one value. So this is the most important concept that you are using when you are finding the roots using the De Moivre's theorem, right? So in which case, if you raise a complex number to the power of, say, n, or 5 or 6 or 7 or 8, then you had only one value, which we just did, like we did 1 plus I to the power of 5 or something like that. Then you have one value here, a plus ib, that's it. But when you are raising this to the power of 1 over n, you should be having n different values. By the explanation I did here, you should be having n different values. So if you give the answer just like this, then you are not giving n different values. So if you have, say for example, 1 over 5, then it will be r to the power of 1 over 5 theta over 5, which means you are giving one value. No, this is wrong. So it should be n, and in the side the n should take the values 0, 1, 2, 3 up to n minus 1. Okay, that means you are having 1, 2, 3, 4 n values of from this equation. You will see that how this is applied. Okay, let's take an example of 1 plus I root 3, which we have already done, and let's say I want to find 1 over 3. So you can say that you want, in other words, you will be asked to solve the equation where z cube equal to 1 plus I root 3. This is also the way that the question could be put up. You solve for z power 3 equal to 1 plus I root 3, which means that you are solving for z, which is equal to 1 plus I root 3 to the power of 1 over 3. So as I said, you need to take 1 plus I root 3, and you need to convert this to r cis theta first, right? So r cis theta for this would be, r would be 2 as we did before, and theta we have seen that it's going to be pi over 3, which is 60 degrees. So your r cis theta would be 2 cis pi over 3, and again this here you cannot use pi over 3. If I use, let me do it as you would. If I use this z equal to r cis pi over 3, that is 2, I'll write it as 2 cis pi over 3 to the power of 1 over 3, then I would be getting 2 to the power of 1 over 3, and cis, which is cos and I sine, pi over 9, and I'm not getting three different values here. I'm just getting one value, one particular value. So this is wrong. You cannot take it like this here. This is wrong. So there is some mistake in that. So our argument was pi over 3 and this is 2 and the question was I 1 plus I root 3. So keep it here. The mistake is in this. What you need to do is, we just saw that if it is pi over 3, you will get the same value again after every 2 pi rotations. So the same value is got when you rotate it 2 pi times more and more, right? So this is also equivalent to saying theta is equal to pi over 3 plus 2n pi. How many ever 2 pi's you add up, you get the same values. So it could be pi over 3, it could be 2 pi plus pi over 3, it could be 4 pi plus pi over 3. So you can have n ranging from 0 to any number. So in this case, that is what you are supposed to do. How many n's you are going to substitute? If it is to the power of 1 over 3, then you are taking 3n values. So you are going to stop with n equal to 0, 1, 2, 3, 1, 2. If it is to the power of 1 over 10, then you should go up to 0, 1, 2, 9. So this is the catch for this De Moivre's theorem. Using De Moivre's theorem, finding the root of a complex number. Okay. So you just don't, again I'm repeating, don't give the answer as pi over 3. Convert it to plus 2n pi, where the n ranges from 0, starts from 0 and goes on depending on the number which is in the root. So here we are having 1 over 3. Therefore your question would change to 2 cis pi over 3 plus 2n pi to the power of 1 over 3. So our principal value here changes to plus 2n pi, where immediately you write what are the values that n should take. Here in this case it's 0, 1, 2 because there is a 3 here. I need 3 values here. So 2 to the power of 1 over 3 and cis pi over 9. I'm bringing the 1 over 3 using De Moivre's theorem for n is equal to 0, 1, 2. So which means it is 2 to the power of 1 over 3 cis, when you substitute 0 it is pi over 9, and the second value is 2 to the power of 1 over 3 cis, when you substitute n equal to 1 you get pi over 9 plus 2 pi over 3, and the third value would be when you substitute n equal to 3, which would be pi over 9 plus 4 pi over 3. You can simplify all these two numbers and give 3 answers. One, this is first value, second root and the third root. You have 3 roots now. Okay, hope that was easier. The next part would be solving polynomial equations whose roots are complex numbers. If z is a root of p of x, that is if p of z equal to 0, then p of its conjugate is also equal to 0, which means that both z and its conjugate always are the roots of the polynomial given. Okay, that you have to keep it in mind. That is, if a plus ib is a root, then a minus ib would always be a root. If z equal to 1 minus I is the root of the is a root of the equation, which is 2z cube minus 7z square plus 10z minus 6 is equal to 0, then find the other roots. So there is only one root given and you need to find the other roots. Immediately once you see the complex root, then you can see that 1 plus I is also a root for this equation, which means that z minus 1 minus I times z minus 1 plus I would be a root. So which is actually z square minus 2z plus 2 would be one of the factors, and times, that means this divided by, I can write it again, I'll write the equation again. This is one of the factors of this equation, 2z z cube minus 7z square plus 10z minus 6 has one factor as this quadratic, which means that this divided by z square minus 2z plus 2 should be giving you the third factor, which gives you 2z minus 3 on division. So 2z minus 3 is the third factor, which means that z equal to 3 over 2 is the third root. So we have three roots here, which is 1 minus I, 1 plus I, which was direct from here. For finding the third root, you need to make the factor using the first two roots and divide the given equation by the factor that you have got. Then you get the third factor, and from the third factor you get the value, the third root of the equation. Okay, so we'll have one more question on this. Just solve. You are not given any hints. Solve z cube minus 4z square plus 9z minus 10 equal to 0. So if you are given one of the conjugate roots, then you can always get the second root as we did now. But none is given here, which means that you need to look for the first real root. So for all cubic equations, you'll have one real root, and the next two roots could be real or both complex. So naturally you have to have one real root anyway. Therefore you can go in for the real root trial and error method. In this case, z equal to 2 satisfies this equation. Therefore z minus 2 is a factor. So what you need to do is you need to divide the given polynomial by z minus 2, and you'll get a quadratic, which is z square minus 2z plus 5, and you need to solve this. Solving these type of equations is always comfortable with the quadratic formula, which means minus b plus or minus square root of b square minus 4ac over 2a would be easier for you. 2 plus or minus square root of 16 over 2, which means 2 plus or minus 16. Okay, 4i over 2, which means it is 1 plus or minus 2i. So you have the other two roots in complex form, and you can see that you get the conjugate roots there. So that's all with complex numbers. All the best.